have a problem. For the cell, a cell is given, that is cell representation is given, which is zinc solid, which is electrode, then Zn2 plus in solution, and there is salt bridge. After that there is general expression of any metal M, and the oxidation state is X plus. Now the M, it may vary, and X, that may also vary depending on the nature of M. So different half cells and their standard electrode potential that are given. So here Mx plus M system, it may be gold 3 plus gold, and for which the value is 1.40. Then for silver plus silver system, the value is 0.80. Third system is iron 3 plus to iron 2 plus, and for it the value is 0.77, and Fe2 plus to iron, that is minus 0.44, and zinc is constant. So in the anode side there is zinc, so always there will be oxidation, but in the right hand side there is cathode, and in cathode there may be different types of metal. So we have to find out that which cathode, because cathode is changing, anode is fixed. This is anode which is fixed. So as cathode is changing, so which cathode will give maximum value of E0 cell per electron transfer. So how to calculate that? How to understand that in which case it will give maximum value? So what we will do, for each system we will find out the E0 cell. So for the gold system, the E0 cell will be, for gold, so first I will write the cathode value, that is 1.4 minus 0.76. Okay, so this will be 6, 2.16. Then we have silver system, for which E0 cell will be 0.8 minus will be cancelled. I am directly writing 0.76. So obviously this value will be less because it is lesser than 1.4. And for the third system, that is iron 3 plus to iron 4 plus, 2 plus, here E0 cell will be 0.77 plus 0.76, which is even lesser than the silver system. And for the last one, Fe2 plus to Fe, if this system is present in cathode, then E0 cell will be minus 0.44 plus 0.76. So this is even lesser. So basically this is least, the last one, and maximum we can see it is for gold. Actually even we don't have to do the calculation, just look at the values of all the electrode potential which is for cathode, and that is given. So it is easily understandable that 1.4 is the maximum value among these four. So obviously when we will combine these two, it will give maximum value of E0 cell, and that is asked in here, asked in the question. So correct option will be Au3 plus Au system. Among these four, this will give maximum electrode potential. Next problem. Okay, here we have to see the relationship between Gibbs free energy and cell potential. But why it is important? It is important because until now what we have done, we have calculated standard electrode potential. So always there is a naught sign, that is E0 of the cell. But suppose if the condition is not standard, then how we will get the electrode potential value? Because magnitude of electrode potential, that is dependent on some factors. So temperature, in the standard state we have fixed it to 25 degrees centigrade, but it may not be so. Then nature of electrode and concentration of ions. So all these when fixed, then that is at standard state, then we can compare the different values. But if this is not fixed, mostly what happens, temperature is fixed, that is fine in most cases. Nature of electrode, that is also fixed, but concentration of ions may change. So when there is different types of concentration, then how the electrode potential will change and how we can calculate that, that we have to discuss. But before that, we have to know what is the relationship between Gibbs free energy and cell potential, because when concentration is changing, that is E cell, which is not a standard condition, it is E cell at any condition, that we can find in from Nernst equation. But before going to Nernst equation, first we will see this thermodynamic discussion which is related to Gibbs free energy, and how Gibbs free energy is related to the E value. We will see that first. So variation of electrode and cell potentials with concentration of ions in solution. So here what is changing? Electrode and cell potential, and temperature is fixed. Okay, so how we can obtain? It can be obtained from thermodynamic consideration. So here we have taken a general equation which is M1A plus M2B. Product is X and Y and coefficients N1 N2 respectively. So this reaction is occurring. So for this particular reaction, the Gibbs free energy change from thermodynamics, we can get this relation. So del G is equal to del G naught 2.303 RT log base 10, and here instead of concentration, here we have the activity of all the species. So in the numerator you will see that activity of X to the power coefficient N1, activity of Y to the power N2. Basically, if the solution is dilute, then activity can be replaced by concentration. Activity is effective concentration. Fine. So suppose there is a concentration 1 molar, but actually in the medium it may not be 1 molar, because in the solution what happens, there is ion-ion interaction, there is ion H2O molecule interaction. So as a result, the actual concentration of free ion which is able to take part in reaction, that is decreased from the actual theoretical value. So actual theoretical value is 1 molar, but in the medium, in the solution medium, because of some other interactions, the actual free ion which can undergo reaction, that is decreased. So that is why there is a term used which is activity. But for dilute solution, this type of interaction will be very less. So whatever is the actual concentration, theoretically we can directly put it here. So here we have activity, but we can replace it by C also. So then it will be Cx N1 C by N2 divided by concentration of species A. So in the denominator it will be the reactant side, coefficient M1, concentration of B, coefficient M2. So for dilute solution, A can be replaced by C. So this is the relationship between del G and del G naught. So this is at standard condition and this is at any condition, because now here we have after log different concentration of product and reactants. Okay, so when we will combine these two values, that is del G naught, that is fixed, but when we will combine this value, then we will get different del G value. So in thermodynamics, this Gibbs free energy, this is very important term, because it is the thermodynamic potential that measures the maximum work done, maximum reversible work done that can be performed by a thermodynamic system. So that is why it is important, because from del G value we can get the idea of maximum work done. Okay, and remember it is at constant temperature and pressure. So in electrochemistry, the maximum amount of electrical work a galvanic cell can do, again at constant temperature and pressure. Now the relationship is electric work that is equal to amount of charge into cell potential. So when we have discussed cell potential, that is E cell, there we have seen that it is actually joule per coulomb unit. Okay, so basically now you can see electrical work, the unit will be joule and this is coulomb. So here also it is electrical work divided by amount of charge, that is joule by coulomb. Now what is NF? N is the number of moles and F is Faraday, that is a particular value of charge. Okay, so for 1 mole there is, if we are saying that it is 1 mole electron, then the corresponding charge will be 1 Faraday. So if there are n mole electron, then it will be NF charge. Okay, remember, for 1 mole of electron the corresponding charge is 1 Faraday. So that is why here total charge will be NF. So this is the amount of charge into cell potential, and this is equal to NF E cell, which is this electrical work. Okay, now this electrical work, this is also equal to the Gibbs free energy. Okay, so keeping this factor common, now we can get some relation between del G and NF E cell, because del G is related to electrical work and NFE, that is electron potential, that is also related to electrical work. So that is why now we can get relation between Gibbs free energy and cell potential. Okay, so what is the relation? So electrical work, that is also equal to decrease in Gibbs free energy. So this is equal to minus del G. So from these two relations, that is in the previous slide we have seen electrical work done is NFE cell and electrical work is also minus del G. So minus del G will be NFE cell. And if the conditions are standard, then it will be replaced by del G naught minus NF E naught cell. Negative value you can keep in left hand side or right hand side, that is not important. Okay, but this is the relationship between del G and E, and when it is standard condition, there is a naught sign. So now we can say that E naught cell, that is equal to minus del G naught by NF. Okay, now suppose we have the reaction A reacting with B, and then we are getting C plus D. So for which we have calculated E naught cell, which is minus del G naught by NF. But now suppose I have multiplied both sides by 2. So here del G naught, that will be converted to 2 del G naught, and NF value, that will also be changed, that will be multiplied by 2. Okay, because del G, that is Gibbs free energy, that is extensive property. So when you are changing the amount of the reactant, then obviously the del G value, that will be also changing accordingly. But as this is the ratio, that is when you are multiplying 2 will be before del G naught and it will also be before NF naught. So ultimately what happens, 2 will be cancelled. That is any number, if it is 2, 3, half, fraction, anything, it is always same and it will always be cancelled. So ultimately the E naught cell that we are getting, that is del G naught by NF. That is, it doesn't matter whether you are multiplying it with 2, 3 or fraction, anything. So it proves that E naught is intensive property. And what is intensive property? This intensive property, extensive property, these terms are basically from thermodynamics. Okay, so extensive property, which depends on the amount of substance, but intensive property, it is not dependent on the amount of substance. And remember, E is intensive but del G is extensive. Okay, so whenever we will have any equation which is multiplied by 2, that does not mean that we have to change the E value also, because it is intensive property. Here we have a problem. So what information is given? E naught of Cu2 plus Cu is given, and another system is Cu plus to Cu. So when it is 2 plus 2, 0, the electrode potential given 0.34, and when it is plus 1 to 0, it is 0.5 to V respectively. So we have to find out the E naught of Cu2 plus to Cu plus, and 4 options are given. So we will write the equations. So don't think it is any cathode or anode reaction. It is not that. It is something different. So see how to do this problem. Cu2 plus, it is accepting 2 electron and it is converted to Cu. And what is the corresponding E naught? It is 0.34 volt. And when Cu plus is accepting 1 electron, then also it is converted to Cu. Now the value is 0.522. This is equation number 1. This is equation number 2. Now if we subtract equation 2 from 1, negative, negative, negative. So Cu will be cancelled, and here in the left hand side we will have Cu2 plus 2 electron minus 1 electron, it will be Cu 1 electron, and this Cu plus it will be now on the right hand side. This is equation number 3, and basically we have to find out the E0 for equation number 3, right? That is unknown. Now we will consider here that for the first reaction, the value of Gibbs free energy del G1, this is del G2, and this is del G3. So see, here we have not written the equation that we have done in case of redox reaction. That is, one system is undergoing reduction, another one is oxidation. So in that case what we do, there is electron on one side, and for the other equation electron on the other side. So 2 electron from both sides cancel, but here it is not cancelled. Here from these two systems, we are by combining these two systems in such a way, we are combining so that we can get this equation, for which we have to calculate E0 cell. Now here how we have arranged the equation, we have done 1 minus 2, but it is not necessary, it can depend, it may be 1 plus 2 or 2 minus 1. Okay, so you have to arrange these equations that are given in the question in such a way so that you can get the system for which we have to find out the E0. So now we know the del G1, del G2 and del G3. So del G1, that will be equal to minus N1 F, E value is 0.34. So suppose this is E1. So here N1 is 2 because 2 electron involved. So it will be 2F into 0.34. Then del G2 minus N2 F E0 2. Now here electron involved only 1. So 1 into F into 0.522. And del G3, number of electron involved here also 1. Suppose this is N3F E03. 1 into F E03 we do not know, that we have to find out. Okay, now from this equation, as we have subtracted 2 from 1, and del G1 and del G2, these two will be related to each other, that is they are related to del G3 in the by this equation. So del G3 will be equal to del G1 minus del G2, because we have subtracted 2 from 1, then only we have obtained 3. So now here we will write minus F E03. Actually F will be cancelled, and this is minus 2F 0.34, then minus another minus F into 0.522. So F, all F are cancelled, right? And here we can also, okay, let the negative sign there. So it is minus 2 into 0.34, 0.68, and minus minus will be cancelled. So it will be plus 0.522. So the value is minus 0.158, but minus minus will be cancelled. So ultimately E03 will be 0.158 volt. Okay, so in this way we can solve this question. So correct option is this one. Now there is another way you can do it. Suppose we have written Cu2 plus, then Cu plus, then Cu, right? Now when we are moving Cu2 plus to Cu, this value is 0.34. When we are moving from Cu plus to Cu, this value is 0.522. But we need this value, which is unknown. So how we can get it? See here, for this system it is 2 plus 2 0, so that is why multiplied by 2. And for plus 1 to Cu, it is only 1 electron, so it is multiplied by 1. So now this is the range. So you can get the value of this portion only if you subtract this 0.522 from 2 into 0.34. So you can, if you are comfortable, you can also draw this type of diagram and you can solve the problem. It is up to you, whichever way you find it better. Okay, answer in any case you will get 0.158. So here by the relation, that is del G is equal to minus NF E naught, this equation we have used to solve the problem. Okay, another problem. Here a cell is given. Now see, this is very interesting. In both sides it is same system. And what is the difference? The difference is only that in the left hand side the CO2 plus concentration is C1 molar, and in the right hand side CO2 plus concentration is C2 molar. That is the only difference. Okay, and change in Gibbs energy, that is del G, it will be negative under which condition? So here 4 different conditions are given. So what is the relation between C1 and C2 under which del G can be negative? Now from the relation del G negative, it means what? That E must be positive. Okay, because del G is related to E by already a negative sign there. So E, if E is positive, then only del G value can be negative, because N and F is never negative. Okay, so what we will do, first of all we have to see the equations. So in the anode side, the reaction that is taking place, Cu is converted to Cu2 plus, and here it is aqueous solution, that is ion, that is aqueous, and here it is written A, because in both cases it is Cu2 plus. So if we do not, we are not marking it separately, we will be confused. So this is for anode, and in cathode this is C. So here it is 2 electron, it is coming out from copper, and here these 2 electron will be accepted by Cu2 plus and it will be converted to Cu. Now 2 electron from both sides, it will be cancelled. So in the overall reaction, in the left hand side what we have? We have the Cu2 plus species, which is from the cathode side. Now from the cathode side the concentration is C2M, and in the right hand side we have that copper 2 plus ion, which is basically from anode. That means it is having concentration C1 molar. So this is C1, this is C2. Next we will apply this equation. Okay, so del G is equal to minus NFE. So if del G is negative, del E cell must be positive. Now here we have used Nernst equation, though how from del G value we can get this equation, that we will see shortly. But right now just see, this is the relationship that we have to use. This is actually Nernst equation. So E naught cell we will consider 0, because when it is same system, because both are same system, Cu2 Cu2 plus. In the previous question what we have seen, what is the value for the reduction potential of Cu2 plus Cu system? It is 0.34. So when we will calculate the E naught cell is basically 0.34 minus 0.34. So it is 0, because it is same system. So it is 0, and here 2 electron involved. So that is why we have written 2F and then ln C1 by C2. Now remember, product side will be first, that is product concentration divided by starting material concentration. So in the starting material side, left hand side, we have C2. So that is why C2 is in the denominator. Fine. Now E cell, it will be equal to RT by 2F ln C1 minus C2. But if E cell, we have to make it positive. So that is why this negative sign, if we remove, that means now we have to interchange the position of C1 and C2. Then only the negative sign can be removed. Now E cell is positive. It is only possible if at RT by 2F it is already positive. Okay. So ln C2 by C1, if this ratio is not positive, that is more than 1, if it is fraction, then it will be having negative value. But if it is greater than 1, that is some whole number, I mean greater than 1, that is C2 is greater than C1, then only this ratio will be greater than 1, right? Under that condition only EoCell will be positive. Now we have found that C2 is greater than C1, but we have not established any relationship between C2 and C1. We just only know that C2 is greater than C1, but this information is enough to choose which option is correct, because in the first option these two are same, which is not possible according to this condition. Then in the second option C2 is C1 by root 2, that means here C2 is less than C1, right, which is again wrong. In the third case C1 is equal to 2C2, that means again C1 is greater than C2, which is not possible. But in the last option C2 is greater than C1, because now root 2 is multiplied, and this condition, it is matching with the condition that we have found here. Okay, so that is why this relationship will be correct. So correct option is option 4. Okay, so whenever this cell representation, it is to some extent different, because here we have same value, so that is why E0 cell, that is 0. But here we have to find out what is the sign of E cell, that is to make E cell positive, what should be the relationship between C1 and C2, because we have to make del G negative, and if del G is negative, E must be positive, and for E to be positive, C2 must be greater than C1, and that is possible only in option 4. Now we will see the relationship between Gibbs free energy and work done. So the relation we have already seen, that is electrical work that is equal to negative del, it is actually decrease in del G, but here we have not given any sign, but it may be negative, it may be positive, so that is why we have not given any sign. So we will basically compare that when this del G value is negative and when it is positive, what is the different conditions, that is different conditions in these two separate cases, that we have to discuss here. Okay, so when the cell does electric work reversibly, only an infinitesimal current is drawn from the cell, very small amount of current is drawn from the cell, and that is the condition for reversible work. So under that condition, the free energy is equal to the electrical work done. Now this equation, it can lead to two different possibilities. Okay, we will focus on them separately. So the first condition is when del G of the system is negative. So del G negative means here we will have W electric equal to minus del G. So it means, what is the significance? The system is doing electrical work on the surroundings. So that is why for the system del G is negative. It is not that the del G, overall del G is negative. It is del G of the system is negative. So this result in transfer of electrical charge in the outer circuit. That means the cell is now generating electric current by some chemical reaction. So that means here chemical energy that is converted to electrical energy. Okay, and this is possible that you can see, you have already seen in galvanic type of cell, where we use some spontaneous reaction by which we can generate electrical current. Okay, so chemical energy is converted to electrical energy, and whenever we will get this, you will see that W electric, it will be minus del G. So this situation corresponds to the operation of a galvanic cell to produce electric current. Okay, for example, the Daniel cell, where we use zinc Zn2 plus Zn couple and Cu2 plus Cu couple. Now another possibility is also there if del G is positive. Now when it is positive, no electrical work is done by the system. Obviously, if in the previous case system is doing work, here it is not doing any work, so no electric current is generated. So how we can make some change? The change can only be affected only when the surrounding is doing some electrical work on the system. So this is another process. Remember what we have discussed in case of electrolysis of NaCl in aqueous condition, in molten condition, which is not spontaneous, but as the reaction is non-spontaneous, so that is why we are providing electrical energy so that the non-spontaneous reaction is possible, it can take place. So now electrical energy is converted to chemical energy. So this is the reverse process of the previous one, if we compare with the previous one. So this situation corresponds to the process of electrolysis. So we have seen that there are two types of cell, galvanic cell and electrolytic cell. So this is the example of the second cell. Okay, so remember the relationship that we have seen in the previous slide, that is W electric equal to negative del G. This is only for galvanic cell, because here the reaction is spontaneous. Okay, but there may be another case also, though mostly we will be focusing on this galvanic cell. That will be the main topic of discussion. But you should also remember that in case of electrolysis the situation is opposite. Okay, now we will see the Nernst equation. So this equation we have already seen, the relationship between del G and del G naught. So now we will put in place of del G, that is equal to NFE, that is minus NFE. Here we will have minus sign, and del G naught, that will be equal to minus NFE naught. So now we have written the value of del G and del G naught here. The rest of the portion there is no change. Okay, now what we will do, both sides we will divide it by NF. Then NF will be cancelled for this two term, and in the denominator of this term there will be NF. So now the equation is changed to this form, and in this form we have also, what we have done, this negative sign, it is converted to positive. So both sides, suppose we have multiply, if we bring negative charge, then ultimately these two will be positive. So E cell positive, E naught is positive, and this sign will be negative. Okay, now 2.303, then n value will depend, that is depending on the reaction, that is how many electrons are actually involved. But here some constants are there, which is R, which is constant, temperature is constant at 298, and Faraday value, that is also constant. So if we put the values of R, T, F, and then if we combine all these and do the calculation, then there will be a particular number which we can put directly instead of this large term. Okay, so we will now put the values of R, which is 8.314 joule per Kelvin per mole. So all are in SI unit. T is 298, that is 25 degrees centigrade, and Faraday is 96500 coulomb charge, which is for 1 mole of electron. So 2.303 multiplied by 8.314 multiplied by 298 divided by 96500. If we do this calculation, it will be 0.059. So now the equation will be simpler. E cell is equal to E naught minus 0.059. You can also neglect this one. Number of electrons involved, then log 10, the activities of the reactant site, product site, and in the denominator it is the reactant site. Activity can be replaced by concentration for dilute solution. So finally we are making it more simpler here, simply product concentration. So whatever species will be present in the right hand side, we will write it first, and then in the denominator all the species that are present in the left hand side of the equation, that has to be written. Okay, So this is the Nernst equation, very important equation. We will see the use of this equation in different way. Relation between standard electrode potential and equilibrium constant. Okay, so this is very important application, we can say, which we can get from this relation and this relation. So the second relation, that is del G naught, which is equal to minus RT ln K, this relation we can find from thermodynamics. Now as del G naught is equal to minus NF E naught cell, so in place of del G we can put this value, negative negative will be cancelled, and ultimately E naught cell will be equal to RT by NF ln K. So this K is basically equilibrium constant. So if the value of E naught cell is known, we can easily find the value of the equilibrium constant. Now put the values of RTF, and ultimately it will be reduced to 0.059 by n log 10K, because here when we have changed ln to log, then we have to multiply 2.303. So this is the relationship between the equilibrium constant and electrode potential at 25 degrees centigrade. Remember, it is always 25 degrees centigrade because we have considered it 298 Kelvin. So this is one way by which we can obtain this type of relation between E and equilibrium constant, but there is another way also we can obtain this equation, and that is from Nernst equation. So from Nernst equation, this equation we have just established and we have seen it. So in this equation, what we will do, we have considered E cell 0, because at equilibrium it will be 0, and it is equilibrium constant, so it must be 0. So now it is 0. So E naught cell and rest of the portion as it is. Next, E naught cell we can bring in the left hand side, or you can bring it in this side, that is this total term. So ultimately E naught cell will be equal to this 2.303 RT by NF log 10 Kc, that is equilibrium constant basically. So putting the value of RTF and multiplying it with 2.303, ultimately we will get the same relation. Okay, so this relationship is also important, because when equilibrium constant is given, you can find the electrode potential, and if electrode potential is given, then also we can find the equilibrium constant. Okay, so here putting the values of RT and F, then only we can reach to the equation 0.059 divided by n, then log K equilibrium. So this problem is related to equilibrium constant. Okay, one reaction is given which is disproportionation type of reaction. Now what is disproportionation? Disproportionation is when same species is undergoing reduction and oxidation simultaneously. So Cu2 plus 2. So one Cu plus is reduced to copper 0. Another Cu plus is oxidized to Cu2 plus. So this is oxidation, this is reduction. Okay, so for this disproportionation reaction occurring at 298 Kelvin, what is the value of ln K? Read the question very carefully. It is not asking for what is the value of K, it is asking what is the value of ln K, and that is also when you are expressing it in this form, that is you are expressing ln K in the form there is a dash and then 10 to the power minus 1. So you have to find the answer in this form, and then only you can compare with it, and you can say what will be the value of ln K when there is a 10 to the power minus 1 already there. Here E naught value for two system is given. One system is Cu2 plus to Cu plus, another system is Cu plus to Cu. So for both this process, the corresponding standard electropotential that is given, and RT by F, what is the corresponding value, it is for the simplification of calculation it is given. Okay, we have to find out the equilibrium constant. We already know what is the relationship between E naught and ln K, that we have already seen in the last slide. But before that, what we will do here, we will find out what is the value of E naught cell, because if you know E naught cell, then only you can use this equation, right? So for this equation, the E naught cell will be E naught of Cu plus Cu minus E naught of Cu2 plus Cu. And why it is so? It is very easy to understand. See, suppose the first equation that I am writing, copper plus is accepting 1 electron, it is converted to copper. And another system is Cu2 plus, it is accepting 1 electron and it is converted to Cu plus. This is number 1 equation, this is number 2 equation. For the first, actually, why I have written these 2 equations, because see, E naught of these two system is actually given. One is Cu2 plus to Cu plus, that is the second one, it is 0.16, and this one is 0.52. Now the disproportionation reaction which is given in the question, how you can get this equation? It is possible only when you are subtracting Cu, that is the first equation, you are subtracting 2 from 1. Okay, so subtracting 2 from 1, then only we can get the equation which is present in the equation, because electron will be cancelled. Cu plus, it will be on the left hand side, so now it will be 2 Cu plus, and in the right hand side we will have metallic copper, that is 0 oxidation state, and Cu2 plus. So as we have obtained this equation by arranging in this way, that is 1 minus 2, so that is why here E naught cell, that how we are calculating, we are calculating it as E naught of Cu plus Cu system we have written first, and then we have written 0.16, and we are getting 0.36. Now this similar type of problem we have also done it before, but there we have used del G equal to NFE, right? But here, as the number of electrons are same, so the relationship, that is del G1 equal del G3 equal to del G1 minus del G2, that will also lead to the same result, because number of electrons, because it is NFE 3 is equal to NF E1 naught minus NF E2 naught, because we have subtracted 2 from 1, but here N is same, okay, because all are 1 electron, and F is also same. So basically you are having what, E3 naught is equal to E1 naught minus E2 naught, and also here in the overall equation there is no electron, so that is why directly we can do the relation, but you can also use this equation. Fine, that is del G1 3 equal to del G1 minus del G2, the way we have done it before. So ultimately the E naught cell we are getting 0.36 volt, and we are putting it here. RT value is given, and see, when you multiply 2.303 with RT by F, then we get 0.059. But here, as it is asking ln K, be very careful, it is asking ln K, it is not asking log K. So this value you don't have to use. Here directly RT by F value is given 0.025. So put it here, and number of electrons involved 1, so that is why N is 1, and ln K. So simply ln K will be 0.36 divided by 0.024, which is 14.4. But this is not the end of calculation, because you have to write this equation in this format, then only you can compare with this. Because we need only this value of this portion without 10 to the power minus 1. So without 10 to the power minus 1, it is 144, not 14.4. So the answer will be 144. So this is an integer type of problem. Okay, so read the question very carefully. It is asking first of all ln k, not log k, and also it is not asking k value, a single k value, it is asking ln k value, and also in the format when 10 to the power minus 1 is multiplied separately. Fine. So by applying this relationship between electrode potential and K equilibrium, we can find the value of K equilibrium. So here EoCell is known, but ln K is unknown. The reverse may also be another possibility. Next problem. Standard electrode potential for a cell given 2 volt. Temperature is 3000 Kelvin. Now it is different. We have to find equilibrium constant K for the reaction. Now the equation is given, R value given, F is given. And it is always better whatever value is given already in the question, though sometimes we write the value of R as 8.314, okay, but here it is simply given 8, and we use Faraday value which is not exact, sometimes not exactly 96000, but it is better always use that value which is given in the question, because options are made according to these values. And look at these options. Here K is expressed, that is the value of K is expressed exponential, and then in the power there is some values, e to the power minus 80, e to the power 320, minus 160, plus 160. Okay, so how to proceed? So obviously as we have to find equilibrium constant, EoCell must be known. Okay, now EoCell individually for these two reaction, that is two system Zn2 Zn2 plus and Cu2 plus 2Cu, that is not given. So what to do? Here ln K, the relationship with E0, that we have to write first. So see, it is same, just this equation, only the difference is now we have written EoCell NF divided by RT. So separate value of these two systems Zn2 Zn2 2 plus and Cu2 plus Cu, that is not given, but directly here the electrode potential is given, which is 2 at 300. Okay, so at 300 this R value we will put 8, not 8.314. T will be 300 now, it is not 298. Then N value is 2. Why it is 2? Because here number of electrons involved 2. It is very clear from this equation, but if you are having any trouble, then you have to write the half cell equation and then check what will be the value of N. So N value is 2 and F is 96000. EoCell given, that is also 2 volt. So finally we are getting 160. So here base is E. So if we want to get the value of K, it will be e to the power 160. Suppose if it is log, then base is 10. So if it is 160, in that case K will be equal to 10 to the power 160. But here it is ln, so ultimately K will be exponential to the power 160. So correct option is option 4. So these two problems are related to how we can determine equilibrium constant, because we have just seen what is the relationship between EoCell and K equilibrium. Now so that you can remember very easily, here I have written the interrelations among these three terms: del G naught, EoCell and K equilibrium. So del G naught, put these two values in this triangle, these 3 points. The relationship between del G naught and K is del G naught is equal to minus RT ln K, which we can get from thermodynamics. And this equation, that is del G naught and EoCell, the relationship is minus NF EoCell, and EoCell and K equilibrium, this is the relation. So it is EoCell is equal to, there is no negative sign, 0.0592 or 91 or simply 0.059 divided by the number of electron involved into log K. Remember, this is whenever you are writing it 0.059, it is always log. It is not ln K. Okay, because this value we have obtained by considering 2.303, and you have considered 2.303 means obviously it is log, it is not ln. So from this table we can have a quick idea that when the sign of del G is negative, see, this is del G, it is not del G naught, it is the overall that is at any condition. Del G naught means what? It is at standard condition. But if we have written del G simply without any naught sign, that means it is at any condition, at any concentration. So when it is negative, nature of the reaction will be spontaneous, E cell will be positive. Similarly, when it is positive, it will be negative. That means the reaction is not spontaneous. Okay, so in that case, electrical energy have to provide so that this non-spontaneous reaction is possible. And another condition is del G is 0, and now that is possible only at equilibrium. Okay, because when this is 0, then E is also 0. And remember, when E cell is 0, from this relation, what we have seen? 0.059 by n log K. Okay, so when this is 0, then E naught cell will be equal to this value, which is basically this relation. So this relation is only at equilibrium. Okay, because it is equilibrium constant. But if it is some other condition, okay, suppose E cell, that is this value is not 0, any of these two, negative or positive, that means it is not under equilibrium condition, and in that case this K, which is basically the concentration of the species of product side divided by concentration of species of the reactant side, this ratio, it is no longer equilibrium constant, then it is simply some reaction quotient, that is the ratio of concentration of product divided by reactant. You can call it equilibrium constant only when it is at equilibrium condition, and when it is at equilibrium condition, then E cell will be 0. Okay, now we will see that how we can use Nernst equation to find the EMF. Now we will divide it in two portions, that is when reactions are given and when electrodes are given, that is half reaction of the cell representation that will be given. So here first two examples we will see, which is based on when reaction is given, and look at this reaction. This reaction is one half, it's not complete reaction, it is just one reaction, aluminium 3+ accepting 3 electron, it is reduced to aluminium. So for this reaction, how you can write the Nernst equation? So E cell or E electric, whatever, then it is equal to E naught cell, then 0.059 divided by n. Now n value will be 3, and that is why in the next it is written 3. If E naught value is given, you can put it, but here it is simply written in this form. And in the product and reactant concentration, what we will write? In the product side, we have only aluminium, and remember, the concentration of pure solid and pure liquid are always taken as unity. So this is pure solid. But suppose if there is any gas, pure gas, suppose oxygen is liberated, chlorine is liberated, then you have to consider the pressure. So this is, that is concentration you have to take as 1 only if it is pure solid or pure liquid, but not for gas. But here we do not have any gas, so product side we have written in the concentration of product, in the numerator we have written simply 1, and in the denominator it is aluminium 3+, because in the left hand side we have, in the reactant side we have only Al3+. Now if you are bringing L3 plus in numerator, there must be -1 here, and this -1 can be brought before log, and this negative sign and this negative sign will be positive. So ultimately this will be the Nernst equation for this half reaction. Another similar type of reaction, but now it is not half reaction, right? It is combining two systems. Here chromium is oxidized to chromium 3 plus, and iron 3 plus is reduced to iron 2 plus. So if we want to, you can directly write the Nernst equation. First of all, we will see how we can directly write. So if we want to write directly, then it will be EoCell is equal to E0 cell. And how you will get E0 cell? You can get it from that is, if the for the system, that is E0 of Fe3 plus 2 plus system minus E0 of Cr3 plus Cr system. So here these values are not given, but E0 cell will be equal to this. Why? Because here the reaction which is occurring at cathode, that we have to write first, and at cathode what happens? Reduction happens, and this is the process of reduction. This is the process of oxidation. So that is why for iron system it is written first and then minus the chromium system. So in this way we can get the value of E0 cell if these values are given. 0.059. Now in case of N, what you will write? Because in case of chromium it is 3 electron transfer, but if you consider Fe3 plus to Fe2 plus, it is 1 electron transfer. Then what you will write? 1 or 3? It will be 3. Now why it is so? Because when you are considering the single reactions, this is oxidation reaction, and Fe3 plus accepting electron converted to Fe2 plus. Now how from these two reactions you can get this overall reaction? When you are multiplying this second equation with 3 both sides, because now it will be 3Fe3 plus 3 electron, so electron will be cancelled, and 3Fe. So basically what you are getting, left hand side Cr plus 3Fe, right hand side Fe2 plus and 3Fe2 plus and Cr3 plus. So though at first there is 3 electron and 1 electron, but ultimately to get the overall reaction you have to multiply by 3. So that is why here N value will be 3, not 1. So 0.59 divided by 3, then log concentration of the species which are present in the right hand side. So in the right hand side what we have? We have chromium 3 plus, so its concentration will be written, and we also have Fe2 plus. But see, there is a coefficient, so you have to write the power also. Divided by chromium is solid, pure solid, so it will be taken as unity, and Fe3 plus, that we have to write. Power is 3. So this will be the Nernst equation. So if the concentration of all the species are given and the E0 values of these two systems are given, you can easily find out what will be the value of E cell. Okay, and also suppose if E cell is given, E0 cell is known, then also we can find this reaction quotient. Or suppose if any of these two species concentration is given, then the unknown species concentration, that also we can find out. Okay, so in this way we can use the Nernst equation to find EMF.